Good day. In this module, we're going to be talking about the problem of measurement, how you do it, how you quantify it, and those sorts of things. There are lots of ways that you can characterize any kind of science. Some people say it's the presence of the scientific method. Some people say it's the objective study of nature. But if I had to point to one characteristic of science that sets it apart from other kinds of intellectual endeavor, I would say that it involves measuring things, being able to quantify things in nature so that you can compare them meaningfully from one situation to another. And so there's a whole theory of measurement and units and dimensions that we need to know if we're going to understand some of the concepts that we'll be talking about in the physics course over the course of the semester. One of the important distinctions we have to make is the difference between dimensions and units. And these two terms are often used interchangeably, but in science they have a very, very specific meaning. And we have to be cognizant of that meaning because it will help us in being able to do some of the analyses and understanding some of the concepts that we will be discussing. For example, if you're measuring a room for carpet, it's quite common to say, to talk about the dimensions of a room. But in fact, what you're really talking about are the measurements of a room. Dimensions are something entirely different. Now, the problem of distinguishing between dimensions and units is actually quite a simple one. When someone measures something, when you quantify something, there are two basic questions you have to ask. What are you measuring and how are you measuring it? And when you ask the what are you measuring question, dimensions are the appropriate thing to be talking about then. When you're talking about how you measure it, then units start to come into play. It's not made any easier by the fact that despite this need for precision, physicists have actually two different ways of talking about dimension. One of the most common ways is actually the one that most people think of when they think about dimensions, and that is that if you take, for example, a line between 2 points, that line has a dimension of length, but if you now make a square, you now have two lengths. You have a width and you have a height. Both of those are dimensions. And if you extend this to 3 dimensions, as you might in this imaginary cube right here, you not only have a height, a width, but you now also have a depth. And when you define volumes, you are talking about a space that's enclosed by heights, width, and depths. Physicists also talk about a so-called fourth dimension, and you see this quite often in science fiction type of situations, and that is the fourth dimension is time. Now, physicists approach dimensions in this way for very good reasons. One of the ways in which this use of dimension is applied is in cosmology and those sorts of endeavors. And it's not unusual to see physicists talking about multiple dimensions beyond these 4 elementary dimensions, height, width, depth, and time. For example, physicists have defined as many as 11 dimensions that characterize the measurement of the universe. And when you start getting up into the 11th dimension, then you're getting into areas like string theory. Now, you'll be pleased to know that we're not going to be getting into that here in the physics of life. We're going to be approaching physics in a much more mundane level. And this leads us to the other common way in which the word dimension is applied. And that is to describe a particular property of matter that you wish to measure. And physicists recognize 3 fundamental dimensions of matter and the universe. And these dimensions are length, and the usual convention is to enclose a dimension that you're speaking about in square brackets. In this case, we will symbolize the dimension of length as a bracket, as L in brackets. Mass, and we usually describe that with a capital M enclosed in square brackets. And then the third one is time. which we describe as a t inside square brackets. Now you'll see this is a little bit different from the use of dimension that a cosmologist or someone interested in describing the structure of the universe might apply. In this case, we really only have three dimensions here. We have the length, which we had in the other use of the word dimension, but we also have mass and we have time as well. And these three dimensions are known as the mechanical dimensions of matter. Now, the universe is quantal, that is, it comes in small, discrete packets, and so one of the things that we can do is define a fourth dimension that describes this property of matter, and that is to define quantity. And what we'll do is we will describe that as a capital N enclosed in square brackets. Now, you'll notice here that we're not referring to length or mass with any kind of measure like pound or kilogram or inch or any of those sorts of things. When we talk about dimension, we're talking about the existence of a property of matter. And this is a kind of idealizing of the universe. We're saying that length is something that exists and it's something that can be measured. We're not getting into any issues of how it can be measured. We'll be getting into that in a little bit. The same thing with mass. We're saying that mass is a thing that exists and it's something that we can measure. Same thing with time and same thing with quantity. And so that's the fundamental definition of a dimension. Now, there are all kinds of clever things that we can do with these kinds of dimensional analyses. We'll get into some of the more sophisticated areas when we talk about locomotion. But for now, what I'd like to do is to lay out a series of rules for dealing with dimensions, because one of the things you can do with them is treat them as if they are a mathematical quantity. That is, you can do operations on them. So, for example, we start off with the fundamental dimension of length. And as we said, that comes expressed as an L in a square bracket. But there are lots of things we can do with length. For example, we can calculate an area. And an area is just a two-dimensional space enclosed by one or more, or actually two or more lengths. Now, if we have a square, we have a width, and we have a height. Both of those have dimensions of length. And so what we are talking about here is multiplying two lengths with one another. And that means that the dimension of area, again, we're just expressing something that can be measured, we can express as L squared. And the same thing with volume. If we take our cube that we described before, and we now have a depth. The depth is also a length. And so what we are talking about here is we can describe a volume as the product of three lengths. There are three lengths involved, and what we're going to end up with there is a derived dimension of volume that is basically L cubed. Now, there are lots of different of these derived dimensions. Let's just go through some of them right now, because we'll have occasion to come back to them in other modules and also in lecture. So, for example, let's take some dimensions that comprise multiple quantities. So, for example, let's look at the quantity of density. Density is simply how much mass you can pack into a particular volume of something. So if you have a particular volume of air, it's going to be less dense than the same volume of water. Water weighs more, it's more dense, so there's a lot more mass in there, and therefore density is, again, one of these properties that we know we can measure, but it is a combination of the fundamental mechanical dimensions that we outlined earlier. So in this case, we have a volume, and we already know that the volume is the cube of the dimension of length. But we also know that mass is involved somehow, And in this case, we are talking about mass. It's just a mass that's there. It just exists. And the units of density are going to be the mass divided by the volume, and that is our units, or our dimension of density. Again, we're just stating that this is something that exists and that we can measure. Now you'll see I've written down this derived dimension as a ratio, as a quotient. One of the things that we will be seeing is that the standard usage in modern science is to avoid quotients and to avoid writing things down like this as much as possible. So what we will do then is we will simply say that the dimensions of density are mass, and instead of putting L cubed in the denominator, we will say that this is mass times the inverse of the length cubed, and we express that as L to the minus third power. There are other sorts of these derived dimensions that we can talk about. Here's a simple one, speed, for example. Well, we know that that's going to be the ratio of a distance over a time. And so what we can do is we can express the dimensions of speed as a length times the inverse of time, or length to the time minus 1. Accelerations are going to be something that's very important for us to understand. An acceleration is simply a change of speed with respect to time, and so we can start off by saying we have an acceleration. That is a speed divided by a time, and we already have our dimensions for speed, L times time to the minus 1. But now we have another dimension of time in the denominator, and so we simply multiply that by time to the minus 1. And what we get then are the dimensions of acceleration, which are L times the dimension of t to the minus 2 power. And we can go on. One of the things that we'll be dealing with quite frequently is force and pressure and work and those kinds of things. We'll be getting into that in a bit more detail later. But let's just take force, because it helps us to illustrate this ability to combine dimensions to make new quantities. We know that the force is equal to the product of mass times acceleration. This is one of Newton's laws of motion, and we will be speaking more about that in another module. But of course we can see now here that we have a dimension of mass, and if force is the product of mass times acceleration, we already have acceleration as with dimensions of L, length, times time to the minus 2 power. And so we say that force is something that exists. It can be derived from these fundamental mechanical dimensions of nature, and we can express it in a particular way. And finally, just one more, because we're just going to kick it up a notch here to show how we can keep adding dimensions one to another. A pressure is equal to a force per unit area. Okay, and we have force, we have dimensions for area, and so now what we can do is we can say that the dimensions of pressure are mass times L times dimension of time to the minus 2 power. That's force. And we're dividing that by area, which has dimensions of length squared, but because it's in the denominator, we have to give this a minus sign. And now this gives us now the dimensions of pressure, in which case we write out, we just do the mathematical operation here. Mass stays as it is. Length is now the product of length to the 1 power in the numerator times length to the 2 power in the denominator, or length to the minus 2 power. When you multiply similar quantities with different exponents, the quantity stays the same, but the exponents are the sum of those two things. And so now we have length raised to the 1 minus 2, or minus 1 power, and time stays the same, length to the minus 2 power. Okay, so we can do all kinds of fun things with dimensions. We can explore lots of interesting properties of nature, lots of interesting things that we can measure, and so forth. And one of the most useful things about dimensions is that we can actually treat them as mathematical quantities upon which you can do operations like multiplication and division. And in another module, we'll be talking about how this can be used to help develop a theory of units.